Hello everyone. Today's lesson concerns formulas that we can use as identities to help us resolve problems with multiple angles that are involved. So we'll be talking about sum, difference, and cofunction identities, okay? So the sum difference identities are going to take the form of, let's say we have the sine of alpha plus beta. Okay, so we've got the sine of two angles added together. And that formula breaks down into the sine of alpha cosine of beta plus the cosine of alpha sine of beta. Okay? And I said plus or minus there because it really works for both. So if I have alpha plus beta, it's this product plus this product. If it's alpha minus beta, it's still this product, but now it's minus this product, okay? So how would you use that? Well, let's say, for example, I need the sine of maybe 15 degrees, okay? I can't go to the unit circle and come up with a value for that. Now, I could do some converting and all that, but it's really easy to look at this in terms of, well, what is 15 degrees? Isn't that, if I'm thinking about the unit circle, let's look at that real quick. Look how there's a difference of 15 degrees between 60 and 45 degrees, okay? And of course, we know our sines and cosines for 60 and 45. So if I thought of 15 degrees as the sine of 60 degrees minus 45 degrees, I would now have my alpha and my beta angles, wouldn't I? Okay, so let's put this into our sum difference formula, and I would have the sine of alpha, which is 60 degrees, times the cosine of beta, so cosine of 45 degrees. This is a difference, so the difference matches here with the sine. So I would say minus the cosine of alpha, which is 60 degrees, times the sine of beta, which happens to be 45 degrees, okay? And I'll put that in parentheses so it's easy to see. So now all I have to do is just go to my unit circle, right? Like I said, we know what those values are from the unit circle. So the sine of 60 degrees is 1/2. The cosine of 45 degrees is radical 2 over 2 minus the cosine of 60. I'm sorry, I got that wrong myself, didn't I? That's actually radical 3 over 2 is the sine of 60 degrees, because the cosine is the 1/2 times the sine, which is radical 2 over 2, okay? So when I look at that, I get radical 3 times radical 2 is radical 6 over 4 minus, this is going to be over 4 as well. 1 times radical 2 is radical 2. So that my final answer is radical 6 minus radical 2 all over 4. Okay? So I can take this and come up with an angle representation for something that's not on the unit circle. Okay? So when I think about the cosine, it's going to have an equation similar to that as well. So the cosine of, let's start off with alpha plus beta, okay? So that's going to be equal to the cosine of alpha, cosine of beta, minus, now notice this time they are opposites, right? So the sine of alpha, sine of beta, okay? And I could break down a cosine of an angle through this formula in the exact same process that I did with the sine, okay? Now notice, here the sine is plus, plus, minus, minus. With the cosine, it's plus, minus, and minus, plus, okay? So those are our sine and cosine sum difference identities. And of course, we have the same thing with tangent, all right? So the tangent of alpha plus beta is going to be equal to the tangent of alpha plus the tangent of beta all over 1 minus the tangent of alpha, tangent of beta, okay? So if I'm adding, I have addition in the numerator, subtraction in the denominator. If I'm subtracting angles, then I'm subtracting in the numerator and adding in the denominator, okay? So those are my sum difference identities that I can use to work through variations. And my example here, I had 15. It's not on my unit circle. I can represent it as 60 and 45 and work from that, okay? So, and that's really true of anything on here, all right? I could represent 60 as a 150 minus a 90, couldn't I? Because 150 minus 90 would give me 60. Look, I could do 75 as a summation of 30 and 45, couldn't I? Or I could do 105 with 45 and 60. So just any combinations of these, because I know what my sines and cosine values are, okay? So here is how this is broken down in a formula sheet. Sine, alpha, beta, plus, minus, plus, minus. Here it's plus, minus, here it's minus, plus, and so on, okay? So that shows me how to go about doing something like that. Now, I also have some cofunction identities, okay? So let's look at those. So cofunction identities. All right, oh boy, I can't even spell, can I? So identities. So the first one I want to look at is the sine of 90 degrees minus theta is the same thing as the cosine of theta, okay? And likewise, the cosine of 90 degrees minus theta is equal to the sine of theta. If I go back to my unit circle and I'm thinking of the cosine of 60, I can write that as 90 minus 30, can't I? So cosine of 60 degrees is the same thing as the cosine of 90 degrees minus 30 degrees, right? So what that tells me then is the cosine of 60 based on this formula should be the same thing as the sine of 30 degrees, right? Now let's look at that. If I have the cosine of 60 degrees, that's 1/2, and then the sine of 30 degrees, that's 1/2 as well, okay? So this is just a different way of breaking angles down as I need them as well, okay? So you could say, well, what is the sine of 20 degrees, okay? Well, isn't the sine of that the same thing as the sine of 90 degrees minus, well, how do I get 20? Well, I get 20 by subtracting 70 degrees, and that would be equal to the cosine of 70 degrees, okay? So there'll be times when you're given one of these and you can use it to figure out the other one, but it's this relationship in the middle here. How can I rewrite 20 using 90? Well, I can do it with some other angle, okay? So this will work anywhere on your unit circle, okay? So that's how I can use these cofunctions in working through these type of problems, okay? So let's look at some problems where I'm going to maybe work backwards, okay? So let me separate this. And let's look at a problem. So if I had the sine of 5x times the cosine of 3x minus the cosine of 5x sine of 3x. And how could I write that as just a single trigonometric function, okay? Well, the important thing there is to think about some difference identities, okay? So again, this is something you want to have right beside you while you're doing your work. So I see sine and cosine, cosine and sine. So I look over here, and the cosine is cosine, cosine, sine, sine. So it can't be this one, but look, don't I have a nice little match here with sine, cosine, cosine, sine? So, and again, remember in the sine, the minus is the same thing as a minus. So all I have to do is look at this guy and say, well, you know what? This 5x, that's probably going to be my alpha, isn't it? Isn't this 3x going to be my beta? So 5x, 3x. I can go right back to my identity from before that says the sine of alpha minus beta is equal to the sine alpha cosine beta minus the cosine alpha sine beta. Okay, so I just got to plug this in now. So when I plug that in, I'm going to have the that should be a sine. Sine 5x cosine 3x minus cosine 5x sine of 3x, right? And that's exactly what I had up there. So that tells me this is the sine of 5x, my alpha, minus the beta, which is my 3x. So really, that initial expression works out to be just the sine of 2x, okay? So that's how I can take something, recognize the pattern, and determine what alpha and beta are, so I can break this down to be just one particular trigonometric function, okay? So let's look at another one here. What if I were to have, and I'll separate it, the cosine of pi minus theta, okay? What would that be equivalent to? All right, so I have a difference, right? So I want to come over here and I want to look at the difference of two angles for the cosine function. And so I now know that alpha would be pi and beta would be theta, right? So if that's the case, I want to find my formula and plug that in. So I'm going to have the cosine of alpha, which is pi, times the cosine of beta, which is theta. So cosine theta. It's a difference. When I have a difference, I have addition. Okay? So I'm going to look at the sine of alpha, or sine pi, times the sine of beta, which is the sine of theta, right? All right, so now let's solve that. Well, what is the cosine of pi? Okay, I look at my unit circle. Here's pi. Cosine of pi is -1. So cosine of pi is -1. Well, I don't know what theta is, so I can't simplify that any. All right, let's look at this part. Sine of pi. I go to my unit circle. There's pi. The sine is 0. So I'm going to have 0 times, again, I don't know theta. But, you know, as it turns out, it doesn't matter because it's being multiplied by 0. So this whole term is going to go away, and I'm going to end up with the minus of cosine theta. So the cosine of pi minus theta is really the negative of cosine of theta, okay? So that's the kind of reduction that I can do by breaking this apart when I see that I have a sum or a difference, to get just down to that one nice, simple equation, okay? So let's look at some other types of problems here. Let's say I have the tangent of alpha is equal to -4/3, and alpha is in the second quadrant, okay? So I know in the second quadrant what? The cosine is negative and the sine is positive. And I also have the tangent of beta is equal to -5/12, and it happens to be in the fourth quadrant, okay? Beta is in quadrant number 4. And in quadrant number 4, I know my cosine is positive and my sine is negative. Now, I have to do a little bit of graphing here to help me in all of this, okay? So if I'm thinking about this, what do I really have, okay? So the tangent is 4/3. Well, remember, tangent is what? Sine over cosine, right? So if I look at this guy, he's in quadrant 2, I'm over here someplace, aren't I? My sine is 4, 1, 2, 3, 4, and my cosine is just 3, okay? So if I draw this, I'm going to have this angle, right? Let's look at this one. And I know I'm out 3 and I'm up 4, right? Look at this guy. Tangent of beta is minus 5 over 12, and I'm in the 4th quadrant, okay? So that means I have to be down over here. So the sine, 2, 3, 4, 5, and my cosine, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this guy is going to look like this, okay? So I'm going to go down 5. I'm going to go over 12, all right? Now, here was the problem. Let's go find the sine of alpha plus beta from that information, okay? Well, sine is what? Sine is opposite over hypotenuse, right? Well, I've got the opposite sides for these angles, okay? But what I don't have is the hypotenuse. So I have to go about and do some good old Pythagoras, okay? So here's a side, and here's the hypotenuse. So when I'm looking at alpha, my hypotenuse is going to be the square root of 3 squared plus 4 squared, right? So I'm going to have the square root. This is 9 and 16 are 25. So the hypotenuse here is 5. Okay? Let's look over here at beta. See what we've got on beta. So the hypotenuse for beta is going to be the square root of the sum of the squares of these sides, right? So I'm going to have 12 squared plus 5 squared, and 144 and 25 is 169. So square root of that is 13. So I now know that my hypotenuse, okay, is 13 units. So how can I go about solving this problem? The sine of alpha. The sine of alpha plus beta. Well, what is that? Okay, isn't that a sum difference formula, right? Sine of alpha plus beta. So I'm going to say that is equal to the sine of alpha cosine of beta plus the cosine of alpha sine of beta, okay? Well, what is the sine of alpha, okay? So here is opposite over adjacent, okay, for this guy. And when I look at him, this was the cosine was negative, wasn't it? Not the sine. So the sine of alpha is the opposite over the hypotenuse, or 4/5, times the cosine of beta, okay? So when I'm looking here, sine over cosine, but notice my cosine is positive here. So the cosine is going to be 12 over 13, isn't it? All right, so now I'm going to add the cosine of alpha, all right? So cosine is negative this time, right? So I'm going to have a minus 3/5 times the sine of beta. Well, he has to be negative, okay? I'm in the 4th quadrant, so I'm going to have 5 over 13, aren't I? And this guy has to be negative, okay? So what do I get here? I get 48 over, what's that, 65 plus, because 2 minuses cancel, 15 over 65 for an answer of 63 over 65. And then that would give me the sign of alpha plus beta from this information. So sometimes I have to go to my graph to put it down so I can figure out what these hypotenuse values are. And then it's important to see it so I can see where the sine cosine is positive or negative, okay? So let's look at maybe an identity doing this, okay? So how about if I have the following identity? So the cosine of 4 theta over sine theta minus the sine of 4 theta all over cosine theta happens to be equal to the cosine of 5 theta all over sine theta cosine theta. Okay? So remember what we talked about earlier when trying to verify an identity. We want to look at the most complex side first because that's where we can make things happen, okay? So if I look at this, I'm going to work on my left-hand side. This just seems to be more complex than the right-hand side. I've got 2 fractions here that I'm trying to find a difference for, right? Well, if I want to add or subtract fractions, I need a common denominator, right? So the common denominator between these two is sine and cosine. So if I multiply this guy by cosine theta over cosine theta, okay, I'll get cosine sine. And I would likewise have to multiply this guy by sine theta cosine, sine theta, because I can only multiply when I'm multiplying by 1. So what does that give me? That gives me cosine of 4 theta cosine theta all over sine just typically comes first, all right, minus the sine of 4 theta cosine, sine, I don't know why I want to keep writing cosine down, sine theta all over sine theta cosine theta. All right, let's do our math here. And I've got the same denominator. So we'll just put that numerator on top of, that should be theta, cosine theta minus sine 4 theta, sine theta all over sine theta cosine theta. Okay, so remember, I'm trying to verify an identity, and my denominator now matches what it was I was trying to match. So let's look at this numerator here. I have a pair of cosines subtracting a pair of sines, okay? Now, if I'm doing my work and I've got my formula sheet right next to me, I need a pair of cosines and a pair of sines. Well, look here. Cosine of alpha and beta gives me cosine, cosine, sine, sine, right? So I have a subtraction here. So if I have a subtraction on this side, I actually have an addition, right? Notice here that alpha is going to be 4 theta. Beta is going to be theta, right? So I need to add my alpha and beta. So on this side, I would have now cosine of my alpha plus my beta from my problem all over sine theta cosine theta, right? And I know from this, all I have to do now is add my thetas, and I get cosine 5 theta all over sine theta cosine theta. And look, that's exactly what we were trying to verify at the top. So again, just like always, taking the more complex side and working on it. All I did here was really find common denominators, pull them together, and then through a little pattern recognition, realize that it was the summation of alpha and beta, which was 4 theta and theta. Okay? So what all have we done here today? So we've taken and we've learned about these new sum difference identities and how we're able to do some things with those, okay? And we also talked about some of these cofunction identities and how we can rewrite an angle as a different function with a different angle. And of course, we've got some of these for tangent as well, okay? So anyway, that concludes today's lesson, and I'll look forward to seeing you on the next one. Goodbye.